This is Tuesday, December 1st, 2020, Chemistry CP, Mr. Turek presenting electron configuration notes. This is a PowerPoint that was really first put together by Mr. Centeno, I believe. And now I'm going to talk you guys through it one more time for the sake of learning. Here is an image from an assignment that you students did not do. The idea was eventually you build up a collection of dots on a piece of graph paper. The center of the dot represents the nucleus of an atom. The dots surrounding it represent the possible location of one electron at any given instant in time. The educational punchline of this assignment was for you to realize that when the Earth goes around the sun, it's a very definite particle in space and time, and we can calculate exactly when Jupiter will line up with Saturn as viewed from Earth, because all those objects are particles. When we zoom way in on one atom, like this diagram is showing, the electrons are not like the Earth going around the sun. It's not a definite particle at a definite location in space and time. Instead, it's a standing wave of energy, crazy as that might sound. And at any moment, we can't really tell you where that electron is, but we can show you a probability distribution function like this one that says, well, most of the time, it might be around here. This is a little bit better computer-generated model of the same idea. The center of the sphere would be the nucleus of an atom. The more densely spaced the dots are, the greater the probability that that would be where you find the electron at a given moment. But electrons are crazy critters in that, on the one hand, they can behave as if they are a particle, a solid, very tiny, tiny dot of matter zooming around space and time. But on the other hand, they could also behave as if they're just a wave. Now, if you go down to the beach and you watch the ocean waves sloshing up against the shore, you can see that the waves carry energy able to move the sand around where the wave hits the shore. Electrons can be thought of as waves of energy that are vibrating around the nucleus of the atom. And that is crazy but true. It means they're not really a particle under those conditions. They're spread out, and it's just strange quantum chemistry. We're going to treat them kind of as if they're particles for most of our thinking. This is just a higher quality computer model. Again, the denser the darkness on the paper, the greater the probability that that's where you would find the electron. Now, these models all look like spheres or circles getting denser in the center on this two-dimensional paper. But as we studied atoms in detail, we've grown to understand that there are other shapes to these orbitals. This is great for the s orbital, a little sphere. Other orbitals look sort of like dumbbells, and others look like donuts with dumbbells. So there's a variety to these probability distribution functions for electrons. Crazy, but true. We are going to task you with being able to list the order in which electrons are filled in shells around a given atom. The first thing to notice when you look at the periodic table is that each row represents one energy level. The very tippity top of the periodic table has two elements in it, hydrogen and helium. That is the n equals 1 principal energy level. The entire row below it is n equals 2, and below that, n equals 3, and so forth. This lowest energy level is also the one closest to the nucleus of an atom. So when we do that probability distribution function for hydrogen, we get a little teeny tiny atom. When we do it for sodium, it's a larger shell around that nucleus. As we go farther up, these shells become larger in size. But wait, there's more. Along with the principal energy level, there are subshells within each principal energy level. And they get their names from history, the study of spectroscopy. Today, we don't bother with the names that they came from. We just use the letters. But as a reminder, the S subshell got its name because when spectroscopists studied the light being emitted by atoms, they noticed that these bands of light looked very sharp in their instruments. The P bands of light looked like they followed a simple mathematical pattern, like 1 over n, 1 over 1 plus 1 over 2, 1 over 3, 1 over 4, that kind of pattern. And so they said, oh, these must be the principal lines. So that's how they got their letter name, P for principal. The third set of lines were classified as being blurry or diffuse when they looked at them. And the last set of lines were very, very thin lines when they looked at them in their instruments, and they used the word fine for meaning those thin lines. So there's the historical reason why we don't call this A, B, C, D in the order of the alphabet. Instead, they got their letters from ancient spectroscopy, meaning 100 years ago, S, P, D, F. And we don't even care today in modern times that, oh, that you should know that S meant sharp. But wait, there's more. Each one of these subshells contains orbitals. And that's where we would find the electrons. Each orbital can hold 2 electrons. You are to work out the order in which these electrons fill those orbitals, and that is complicated stuff. I'm going to try to get you to be successful doing it today. I did not give you the blank periodic table to colorize. It still would be a good assignment for me to do. But here is what they would have you do. They would have you colorize the different blocks that you see on the periodic table shape, and then come to the realization, aha, those blocks are a result of these different subshells. First, notice the 2 columns on the far left. They represent the S subshell. The block of 6 dark blue on the right are the P subshell. The 10 columns in the middle are the D subshell. The 14 columns dangling underneath the main periodic table are from the F subshell. I do want to point out that the very top left corner is hydrogen, the lightest element on the periodic table, the only element that has just 1 proton. The next element up is helium. As you can see, it looks as if helium really should be drawn on the second column. Based on its color, it belongs over on the left of the periodic table. Why, oh why, is it by itself on the right column of the periodic table? That is a rhetorical question. The answer is all the elements that are on that rightmost column have one important characteristic in common. And that characteristic is their outermost subshells are completely full. Their energy level is completely full. That makes these atoms extremely happy with the number of electrons that they have. They don't want to lose any electrons because then their shells wouldn't be full. They don't want to gain any electrons because then they would have to open up a new energy level. So these elements on the right column, including helium, are called the noble gases because they have no interest in reacting with other elements, gaining or losing electrons, sharing. No chemical reactions would normally take place between those noble gases and anyone else on the periodic table. So that's why helium is drawn over on the right-hand side of the periodic table, even though technically it's the S subshell that's being filled. For all the others, it's not only that S subshell, but the P subshells as well. All right. Those four subshell letters, S, P, D, F, need to do it in that order. Each one has orbitals. Each orbital can hold 2 electrons. This was an attempt to have it analogous to a house. So down on the first floor, you've got one room. The second floor has 2 rooms. The third floor up has 3 rooms. The fourth and fifth floors each have 4 rooms. Each room can have 1, 3, 5, or 7 beds in it. Each bed can hold 2 guest electrons. So here's the numbering of each floor: 1 at the bottom, 5 at the top. One single room on the first floor is the S subshell. The second floor has an S and a P. The third floor has S, P, and D. The fourth floor has all 4 types, S, P, D, and F, and so does the fifth floor. Great. Now, each orbital can hold 2 electrons. Each subshell contains 1, 3, 5, or 7 orbitals. The S subshell only has 1 orbital. P has 3, D has 5, F has 7. That's why you need to memorize the order S, P, D, F instead of A, B, C, D. And the beds are an analogy to an orbital. And since each bed can house 2 guests, each orbital can house 2 electrons, which is the answer to this question. How many electrons can you fit into the S orbital? 2. In P, 2 times 3 is 6. In D, 5 times 2 is 10. In F, 7 times 2 is 14. Okay, I see I have diligent note takers. I want to pause at this moment and ask anyone want me to restate anything so far or clarify? Ooh, I'm seeing heads shaking left to right, which in North American culture means, nope, we got it all, Mr. Turek, just give us a test. All right. For this, you should have a periodic table handy dandy to look at. Here's one on the screen. You might notice the numbers 1 through 7 on the left side. So that represents the energy levels. The reddish color on the left are the S subshell. Dark blue on the right, or navy blue, is the P subshell. Transitions, light kind of bluish, are the Ds. The greens are the Fs. Now, if you count how many columns, you'll see it agrees exactly with the number of electrons in each orbital. The S has 2 columns. P has 6 columns. D has 10 columns. F has 14 columns. This is not a coincidence. This is explaining why the periodic table is drawn with the shape that it has. The complication for you is that we want you to list the order in which electrons are filled in on the periodic table. So first, a reminder, every box that you see here represents an element. The very first element is hydrogen that goes in the upper left corner. It has one and only one proton. All hydrogen has exactly one proton in its nucleus. Here in high school, we generally think of atoms as having 3 subatomic particles. There are more, and sometimes we study the others, but the 3 main ones are the proton, the neutron, and the electron. Now, if hydrogen has different numbers of neutrons, it's still hydrogen. Hydrogen can have 0, 1, even 2 neutrons. Those are all hydrogens. They're different isotopes. The elements on the periodic table are listed as being electrically neutral elements. And to be neutral, that means for every proton, which has a positive electric charge, there must be an equal number of matching electrons, because each electron has exactly the same amount, but negative electrical charge as each proton. So when I have an atom like hydrogen, if it has one proton, then neutral hydrogen must have one electron so that the positive and negative charges cancel each other and make hydrogen a neutral atom. Forgot what else I was going to say. All right. This arrow represents the order in which these subshells become filled. So the very first subshell that's ever filled always begins with hydrogen. Principal energy level 1, subshell S, 1 electron. Then we completely fill the shell with helium. All atoms start off this way. If there are more protons, then there are more electrons to go with it. And so we begin on the second row, first completely filling the 2s subshell. After it is filled, we then fill the 2p subshell. The analogy I used last period was to say, think of these subshells as being like grocery bags. And you go to the store and you buy a bunch of cans. Each can represents one electron. Now, this grocery store looks at your shopping cart and maybe you've got 10 cans in there. But their policy is they always give you their small bag first. The small bag, the S bag, can only hold 2 cans. But that's what they give you. And they're not going to give you another bag until the one that they give you has been completely filled. So first, they give you a small bag, and you put in your 2 cans. Then we start on the second row. They give you a second small bag. And you grumble and say, wait, I have 10 cans of food. Why don't you just give me a big bag that can hold 10 cans? But that's not their policy. No, they give you a small bag, then they give you a second small bag. After that, they give you a P letter sized bag. The P letter sized bag can hold 6 cans. After you fill the P, if you still have more cans, then they give you a third S small bag. It can only hold 2 cans. This is the strange policy in this grocery store. If you still need another bag, the next one is a pea-sized bag that can hold 6 cans. If you still need more bags, the next one is an S-sized bag. It can hold 2 cans. Now, the shape on this periodic table is slightly misleading. The next bag that they would give you at this point would be this red D-sized bag that can hold up to 10 cans. Only after this red bag is filled would they then give you another blue bag, a P letter sized bag that can hold 6 cans. After that one's filled, another S bag. What a strange and crazy grocery store that hands out bags for your cans in this particular order. Always in this particular order. Okay, so there's all the arrows drawn so far. Now, for a few occasional elements, the order is slightly mixed up. Not in a big way, just in a small way. And that has to do with individual quirks for some occasional atoms. And in the small way, I mean like, okay, their electrons are filled the way their next door neighbor is to their left or right first, instead of what they should be doing. So just small changes. I think we're not going to study those this year. Here is a periodic table labeled with the different subshells. Remember, those are like different sized grocery bags. The names of the elements are displayed. The number of columns for each subshell is displayed. And now on the next slide, we're going to replace the names of the element symbols with the electron orbital configuration. We always start in the top left corner with hydrogen. It's on the n equals 1 principal energy level. It only has one subshell, and that is the S subshell. It only has one proton, So neutral hydrogen has only one electron in that s suborbital subshell. We represent that with a superscript 1. On the far right corner of the periodic table is the element helium. It is also n equals 1 principal energy level, which only has the s subshell. Helium has 2 protons, so neutral helium has 2 electrons. The superscript 2 means we have filled that s subshell. Because it's filled, helium behaves like a noble gas. The next element, number 3, is lithium. It's on the second row down. So its energy level is N equals 2. Here, the grocery store said, oh, you have more than 2 cans. We'll give you a second small bag. So the orbital electron configuration for helium begins by first filling the first small bag completely, 1s2. Now you start filling the second bag, 2s1. The next element, beryllium, 1s2, 2s2. The next element, over towards the right, is boron. Capital B is boron. That has 5 electrons. The grocery store gives you a small bag first, then a second small bag, and now at last they hand you a pea-sized bag that can hold up to 6 cans. And you're only going to put 1 can into it. Crazy grocery store. You're saying, look, if I only have 5 cans, why don't you just give me a pea-sized bag in the first place? But no, that would make life too simple. Your life is destined to be complicated. So here's the third grocery bag they gave you. And they said, don't bother asking us for any more bags until the last one that we gave you has been completely filled. Hence, all these elements on this row, boron, carbon, nitrogen, oxygen, fluorine, neon, go into this pea-sized shopping bag. P1, P2, P3, P4, P5, P6. More cans, you get another S bag. Sodium and magnesium on row 3 get an S bag. Need more cans? And by the way, C, S1, S2. Aluminum, silicon, phosphorus, sulfur, chlorine, argon. Oh, those guys get a pea-sized bag. P1, P2, P3, P4, P5, P6. Have more cans? Potassium, calcium? The grocery store gives you another S-sized bag, a small bag. Oh, man. And at this point, the bell went off. You guys get to take a 3-minute break. Here we go. All right. Here on the periodic table is the order in which things are filled in. And I'm trying to click and advance, click and advance. Here we go. When you look at this configuration, the 5 is referring to which energy level you're on. 1 at the top with hydrogen, down to 7 at the bottom. The P is the letter of one of those four subshells, always in the order of S, P, D, F. The superscript represents the number of electrons that are in that subshell at this time. Now we can add and remove electrons that would create an ion. When we're talking about neutral atoms, adding or removing electrons will make it a different element because we assume that for every electron that we list, there's a matching proton to make it electrically neutral. Okay, let's practice your skills here. If I have hydrogen, it is going to be a 1s1 orbital. Electron configuration, I should say. The next element, helium, is also on principal energy level 1. Therefore, it's in the s suborbital. And the s orbital can hold up to 2 electrons. So there you go, 1s2. The next element, lithium, first fills the 1s subshell completely. That's the first grocery bag. In fact, every element from now on will always begin with 1s2 when we write the long form electron configuration for it. The second grocery bag is another small bag, 2s. Lithium puts 1 can into it. The next element, beryllium, can completely fill the second small shopping bag. So now our configuration is 1s2, 2s2. If I have another electron, now the grocery store finally gives me a larger grocery bag, the pea-sized grocery bag. And they say, okay, don't bother us again until after this last grocery bag has been completely filled. So with 5 electrons, the electron orbital configuration, long form, would be 1s2, 2s2, 2p1. Time for a pop quiz. Giselle, what would be the electron configuration for the next element, which is carbon, that has 6 electrons? Emmanuel, C, do you agree? What would be the electron orbital configuration for nitrogen? Emily. Um. Ah. Jessica, do you agree? Okay. The next element, amber, oxygen. Unmute. Ah! Hannah, do you agree with that? Oh, okay. The next element is fluorine with 9 electrons. Alyssa, try it. Ryan, do you agree? The next element is neon. Esther. Samantha, do you agree? Oh, and I can hear your phone going off in the background there, Esther. Okay. Can anyone tell me what would be the next bag passed out? What would come after 2P? Anyone? Skyly? I didn't understand your response. So after neon, we would have to start a new energy level with a new subshell. So what would be the next subshell after the 2P? Eric, do you agree? Oh man, it would actually be the 3S subshell would come next. 3S. Oh well, we have some work to do, don't we? Yeah, this is one of those crazy things. I know you would expect 3D to be next, but it's not. 4S comes first, and I'm going to try to show you a drawing on the next PowerPoint that helps explain why that worked out that way. But for now, oh, there's the crazy thing, n minus 1, craziness and confusion, and we're not going to do any more with this slide. Okay, I'm now going to stop recording the slide. What button that one is.